you. Can we turn off that light? Can that light right there go down? Oh, okay. Okay, cool. Oh, okay, cool. All right, thank you very much. Can I talk without I need the microphone? Need the microphone. Okay, I'll hold it over here. So I'm gonna my presentation. Thank you for the introduction. It's a pleasure to be here at Silvilaser. First time attending, and it's been a lot of fun. Really amazing group of experts here, and the technology showcased and being compared and stuff is really exciting and a beautiful location. So thank you for the invitation. And I hope to see you in the Silvilaser family in the future. My presentation is both from me. I'm a professor at the University of Florida, and also with my wife, who's also a professor at the University of Florida. We're the co-directors of the GatorEye program and also of my Spatial Ecology and Conservation Lab. So basically, my talk will be about challenges and opportunities for ecological mapping using drones, using a variety of case studies. The focus will really be on the GatorEye system, which probably half the conference went to yesterday and saw working in the field, but then the other half didn't, so I have a brief overview of what we did because I have to admit that I had a 35-minute talk and then I just worked on data processing all night and threw it into the presentation, which is going to have totally thrown everything off, but I don't really care because I think showing you the data that we collected yesterday is more important than showing you examples of case studies that I did in Peru or Mexico or something like that. So, so starting off, let's see here. So I'm going to start by presenting as the first contender in the great Silvilaser Point Cloud Wars of 2019. It was a thrilling event. In summary, we had buses, we got into these buses, we put our gear underneath the buses, and then we drove here to the biological station, actually located directly next to the dam. At first I wasn't aware why there was so much paperwork and so many restrictions and on until actually watching the video at this location. They went on, it's like one of the largest structures in the planet and one of the biggest sources of electricity in the planet. You start to hear all this, you're like, wow, this is probably a lot of multinational security kind of issues going on. Then I looked at Google Maps and it was literally like 500 meters away. In fact, we actually got laser scans of portions of the dam on the edge just by virtue of flying where we were, so that's pretty cool. So it's actually quite a nice area. They gave us a whole setup. There was about 90 people there and walking around through the forest and viewing everything that was happening. For my portion, I'm working with my upcoming postdoc, Gabriel Prata, set up the base station and a hyperspectral sensor here and a PAR sensor. He got to talk a lot about why we set that thing up while I moved on and did other stuff, so I don't know what's going to come out of that. We have a lot of batteries, set up a whole ground station here in the nice shaded portion, and then people started walking up here to a variety of field plots, and also way down here we had a whole bunch more field plots. There was, you're going to hear from different groups who may or may not have data available. I know that at least some of them do, so I'm going to be showing what I collected, and then hopefully other people might be showing what they collected, and it should be really interesting. And I'm hoping for real science to come out of that because it's actual real science grade data by a lot of people and effort. So what do we do? Basically then, somewhere in here is a tiny dot, which is the GatorEye system, and you can't see it, or maybe it's not even there, but I can't remember. So this is the flight plan that I came up with the night before. Basically, these are our plot areas here to the north and another plot to the south. These are very small areas, so each one of these is about 4 hectares. And because this is the Point Cloud Wars of 2019, what I did was I took my entire 15-minute battery flight and I just flew as dense as possible over these plots. So about every 5 to 10 meters doing a grid, and then actually returning and doing it in the opposite direction. I just wanted to see how dense can I get a point cloud, and I was personally hoping for 8,000 points per square meter, which some people laughed at, and I was like, I can do it. And I couldn't do it, and it makes me sad, and I'm still trying to figure that out. But you can see what I was able to do. But you can see that, so basically I did 4 flights. Each battery represents 14 minutes of data collection, or about 30 gigabytes of combined LiDAR, hyperspectral, and visual imagery. So we collected a lot of data yesterday. But between these 4 separate batteries, breakdown, data collection, putting it back together, you know, we can do that with the 4 flights in about an hour and a half. We had multiple objectives going on here, some of which I get into later in the presentation, assuming I even get very far into that presentation. There's multiple objectives. One is try to get as dense point over these small parcels where Chiago and laser scanners and backpack mounted things and like photogrammetry systems, so much stuff. In fact, I don't believe I've ever heard of a study where so many different top-notch systems were simultaneously collecting data. I haven't heard of one, and maybe you have, but I certainly haven't, and absolutely not in like a top national security center, which makes it all the more exciting. So that was goal number one. Typically, I would very rarely fly this close together and this dense because I'm usually trying to understand larger scale regions, almost like landscape type questions. And so for that, basically, I have a standardized flight flow, which is about 75 meters high, probably about 60 to 75 meters apart. With that approach, I can collect a half square kilometer of dense, 90% side lap data per flight. Every 14 minutes, I'm collecting a half kilometer of data. So that's pretty great. So in the first two flights, in order to maximize solar angle, because we got there and it was already kind of late, I flew this big plot. And so the big plot's a really cool thing that I'm doing, or the GatorEye program is doing, is we've been traveling around the Americas and even in North America, establishing what we call big plots. And we're developing a website called the Big Plot Network. Basically, can you establish plots with a drone? Before, maybe not. But when I think of a plot, I think of it from a forestry perspective, meaning that we can have the ability to return to that area and start to get an understanding of detailed multi-temporal changes in ecological parameters that might be relating to ecosystem health, growth, things like that. And so, yes, now that we have such high point density, we're starting to bridge that gap, not only between TLS data, which is where people go because we're comparing systems, but actually I think we're bridging the gap between field data collection, and that's going to be the next step right there. So we're establishing these big plots. I usually aim for 1 or 2 square kilometers, but sometimes we put in 35 square kilometers in just a couple days. And we've got these now all the way down from Mexico, across Costa Rica, Panama, all through Peru, and then all the way across Brazil, including up in Florida and heading up the East Coast there. So we've got a lot of this data sets all around. You can go to my website or our website, GatorEye.org. You can click on our MOU, and basically you can download data as we get it processed, unless it's under embargo for some reason. Unfortunately, the data from yesterday is going to have such an embargo, and I'm going to work with Louise to figure out what that means because there is national security considerations. But if people come and have a good question, a science question, I really think that there's going to be lots of opportunities to get access and do a specific projects with it. So basically, in the first 28 minutes, we established 1.5 square kilometers of what I think is very dense LiDAR data, probably 500 points per square meter, and also hyperspectral data and visual. And then the next two, we put in these ultra-dense plots in order to try to compete in the great LiDAR point density wars with the other systems. So this is a live view of what it looks like when the drone's flying over. This is a 440 meter swath coming down here. So you can see that although we're 75 meters apart here, we're actually getting about a 90% side lap of LiDAR data. And that's by virtue of the fact that the puck is spinning in 360 degrees, and every single one of the 32 lasers has a range of 220 meters. So we're getting really a massive amount of data, massive amount of side lap. And as you'll see, as you won't see at the end of my formal talk, because there's no way I'm going to get there, it's actually really interesting how you can, with a LiDAR system, how it's so different from a photogrammetric system, where you can just take one flight through whatever and get amazing data set. And we've used that to just fly down rivers, to just fly down riparian corridors, and just bam, you get an amazing data set. It's so much different than photogrammetry, where it's like, all right, we got to do 100 passes and we need side laps and go the other way and up and down and see what we get, and then we don't even get the ground. So I think LiDAR is really just killing photogrammetry in a lot of ways, but not for cost right now, and I may or may not get into that. So because there's such a large area and so much data, I'm just going to zoom in here to the northern plot, what I refer to as the northern plot, because it's to the north of where I was launching, where we were based here at the Itaipu Biological Station here. I'm actually using Spatial Explorer software here. This is how we can interact with the post-processed LiDAR data. In order to even get to this stage, I first had to go through a round of Inertial Explorer, the same as if you were flying an aircraft. and then we fuse the base station differential data with the IMU accelerometer data and all the angular data and the GPS on the rover and the drone basically, and we get this excellent trajectories, which is what we got, and I had to deal with the internet to get that. In the end, you can see this is a 1 meter profile going through here. However, I want to point out that this profile is currently limited to 100 points per square meter, just by virtue of this software. It turns out that we actually got 1,500 points per square meter. So what you're seeing here is only 8% of the actual points that we have of this forest. And I only realized that after I took the video, so I still included it. But you can actually start to see trees and stuff in here. It's pretty great. So what I want to show you is, well, okay, what happens if we look at just one image? So this is just one flight, 28 seconds of data, actually about 23 seconds of data passing over a single time, and what we're looking at is the intensity values of the LiDAR data, not the height values, because we haven't done a DEM, we haven't done a canopy height model or anything. So these colors are literally functional, very useful intensity values coming out of this system, and I think that is amazing because, honestly, when I had the VLP-16 before this, intensity stopped being useful at about 20 meters range, and now we're getting really great intensity all across here. In fact, what we weren't able to do before was to actually get good returns over low reflectance surfaces, and now we're getting great dense returns over everything. So I'm really happy with the upgrade that we just did a few months back to the Ultra Puck with the 32 lasers and the range, because the intensity is something that I've wanted to play with. The intensity, as you're all aware, is great. It shoots through the forest, it enters the forest, and if you do some type of a distance correction for that intensity value, I'm curious to see if I can start to distinguish soft surfaces from hard surfaces. How cool would that be? So multispectral LiDAR might be a great future ahead of us, but right now we have intensity values. So could I, this is my question, this is woody material and this is leaf material, and remove the leaves and get a woody biomass map point cloud and just discard everything below a certain distance normalized intensity value, and that's literally what we're going to be able to do quite easily here. This is where we were taking off and flying. So note this looks pretty amazing, but this is 23 seconds of a flight pass. We did 20 passes over every single plot in 2 different directions, and those are combined to actually get a final plot database. So you can see that we get a range of heights. We get a large range of intensity values here, the full range, so those are actually good, usable data values. So that's very cool. So you start to say, well, how good is the quality of these point clouds? So the best way to do that is basically just start laying flight lines on top of flight lines and see how much does the fuzziness increase. Can you still see tree trunks? Are you adding to it, or are you just adding noise? And so, because one flight line, even if you are totally improperly bore-sighted, can look beautiful. It just might be that the ground is at 45 degrees when it should be flat. So, as I'm basically here, you can see that I'm just clicking flight lines on and off, 3 of the 20 that we have going over this plot. And what you see is that as you add additional flight lines, you're not increasing the fuzziness of these surfaces at all. You're increasing the ability to see more and more about the interior forest structure. You're adding smaller branches. You're adding to the oval shapes of tree trunks in the understory. So as you add more, you get more and more definition and the ability to understand the understory. And so what that means is that our bore sighting first is good enough, our trajectory was good enough, that we can now fuse all of our 20 flight lines into a single functional, excellent point cloud without doing flight line matching software. If anybody here has done that type of processing with aircraft, drones, or other things, you can try to statistically match flight lines to minimize uncertainties or differences over different surfaces and kind of force fit them together. You do that afterwards, and you do that because you have done a poor job or your hardware is improper to collect good raw point density to begin with. But we don't even need to do that because already we're able to resolve, for example, differences in DBH and things like that for the trees that are more open. So that was a whole bunch there. So really, given that I was doing this all night, working on this in my room here, without my workstation and everything, and with some licensing restrictions, I'm showing you the best that I was able to do. And I haven't even really been to show you a good example of the full point density. But this little chunk here, and note that I was unable to get the coloration to be all pretty like I could in the other one, just ran out of time. Anyways, what we see here is the full point density of 1,400 points per square meter. Trying to understand the square meter point density can be a challenge when, if you look at a single pass over, the point density is naturally going to be really high under the drone. It's going to get less and less and less as you get further away due to the view angle and everything. So you basically clip a chunk out of the middle of the plot, and now you know what is the actual point density that you're dealing with of that plot. So we ended up with 1,400 points per square meter of real data integrating all 20 of those different flight lines over the plot, and you can see that you get a height, or this is a total height, this is an altitude distribution, not a height distribution, because we haven't done, DEM normalization and stuff like that. So you can see that we have a variety of, the points are distributed across a variety of heights, which is not really topography related, because there's really no topography right there. This is all about tree height differences. We're not getting subterranean points there. So this is this little chunk. Because it's small in this software where I can make it look pretty, I can max out the amount of points at only 500 points per square meter. We have 3 times that point density in the real world. I just wasn't able to show it to you. So pretend that we can have 3 times this point density. That's really what we're doing, but we're only randomly looking at 33%. So this is an example of what we're really seeing in the nursery. Look at this detailed branch structure, not only in the top of the forest, but also going into the understory as you zoom around. You're seeing of course you're seeing the gaps, but you're actually seeing the shape and size of all the different trees. And this is a what I thought to be a extremely dense and very challenging high leaf area type forest. It's short. It's probably about 25 meters tall. You can note here that we're getting extremely dense, even at 33% ground hits. There's no problem whatsoever. We're probably getting 50 to 100 points per square meter or more in ground hits. But then we're also getting all of this detailed branch structure on vertical and other directional surfaces. So this is an amazing data set to really start to understand things like the 3-dimensional leaf area density distributions, horizontally, vertically, even to start to even do polygon or oval type force fitting to these shapes to try to identify in point clouds with woody surfaces and stuff like that. Obviously, it'll be better if we can remove all the leaves by using this intensity value calculation, which is a thought to be done and hasn't been done yet.